Keep in mind that on Thursday, we are scheduled to have our Chapter 6 test, and I will make that available for you on Thursday. I did post a preview along with the solutions on Canvas. Make sure you look over that preview, and by all means, do the Chapter 6 Alex homework and the Chapter 6 quiz on Alex before you attempt the examination. All right, so 6.5 is entitled Determinants and Kramer's Rule. Good place to start is to define what a determinant is. A determinant is a determinant of a square matrix is nothing more than a real number. So a determinant is just a real number. Now, only square matrices have determinants. So, and what's a square matrix? The square matrix is a matrix that has the same number of rows as columns. Okay. So suppose that we look at this 2x2 matrix A. And we say, we use this notation to represent the determinant of matrix A. Looks like the absolute value symbols that we use for real numbers, but the A is a matrix, not just a real number. So when we throw it inside these absolute value symbols, we're asked to find the determinant of matrix A. Some books represent the determinant of a matrix by using this word, DET, short for determinant. And yet some textbooks, the older textbooks, make use of this lowercase delta symbol to represent the determinant of matrix A. All of these are suggesting the same thing. Find the determinant of this matrix. Finding the determinant of a 2x2 matrix is really easy. All you do is you multiply these diagonal elements together. The 1, 1 times the 2, 2 entry. And then you subtract off the product of these diagonal elements. And that's how you find the determinant of a 2x2 matrix. And this will just be a real number. Here's an example. Suppose that we have this 2x2 matrix B, and we're being asked to find the determinant of matrix B. This is going to be nothing more than the product of these diagonal elements. Subtract the product of these diagonal elements. And that gives us 93. So the determinant of that matrix is 93. Any questions how we found the determinant of that 2x2 matrix there? Determinants are, just to name a couple places where determinants are used. Determinants are used in vector calculus when finding the cross product between two vectors, and also in mechanical engineering. Determinants are also used for doing transformations of coordinates in multivariable calculus. And determinants are also used to solve systems of equations, of which we're going to see here. Those are just a couple of uses of determinants. So it's my job to at least expose you to these constructs here. Now, on our calculator, you can check your answer. If you bring up your machine here, and you type in this 2x2 matrix by going into your matrix editing mode. So I'm going to type in this 2x2 matrix that we just worked with here, namely 2, -11, -11, and 7 and 8. Okay, once you enter the matrix into memory, you get out of this second mode to quit, you go back to matrix mode, go over to math, and you use the first function, DET. That's short for the word determinant. So the determinant, you got to go back to matrix, stay on names, and select matrix name A. The determinant of matrix A, enter, is 93. There's your answer. So that's how you can find the determinant of a square matrix using your calculator. All right. And I don't mind, and I would encourage you to check your answer when you're finding the determinant, even if I request that, you do so manually. Make sure that you're able to check your answer. Now, about how do we find a 3x3 determinant? Here we have a 3x3 matrix A. And I'm going to define something else now that we're going to need to know. I'm going to define what the ijth minor of a matrix is. A square matrix is the determinant of the matrix left behind after deleting the ith row and jth column. That's what a minor is. So a minor itself is a determinant. So a minor is just all right. Suppose I want to find the 2-1 minor. No. Okay, I'm not sure what happened. Just got kicked offline. Anyways, to find the 2-1 minor of this 3x3 matrix A, I'm gonna have to delete the second row and the first column. Okay. In the event that I get knocked off the line and I'm not able to return, I will make sure that I upload a video regarding these sections. Okay. But I do apologize for that. All right. So I'm back. All right, to find the 2-1 minor, we have to delete the second row and the first column. And that leaves us with this little 2x2 matrix consisting of the 1, 2, the 1, 3, the 3, 2, and the 3, 3 entry. We have to find the determinant of that little 2x2. All right, so here we go, finding the determinant of this 2x2 matrix that results after deleting the second row and first column. We get the 1, 2 entry multiplied by the 3, 3 entry, subtract the 1, 3 entry times the 3, 2 entry. That is called the 2-1 minor of this 3x3 matrix A. Any questions how we just found the minor of that 3x3 matrix A? That's called the 2-1 minor. Okay. Oh. We look at a specific example here. Given this 3x3 matrix, suppose I want to find the find the 3-1 minor. So to find the 3-1 minor of this 3x3 matrix means that I'm going to have to, first of all, delete the third row and delete the first column. So I'm going to delete the third row and the first column. And therefore, the 2x2 matrix that's left behind after doing that, I'm going to find the determinant of it. So the 3-1 minor of this 3x3 matrix is going to be the determinant of this little 2x2 matrix, 4, -1, -4, 8.
Mine just came back. Is there any way you could go back to the last page? Just I'll take a picture of it and.
Well, it's on the video. I mean,
okay.
I did record it. Okay.
Okay, thank you.
Wait a minute. Hold on a second. Wait a minute. I don't know if it got recorded because I got cut off, so it might have dropped it. But anyways, if we have this 3x3 matrix in general here, okay, we define the ijth minor of this matrix to be the determinant of the resultant matrix after the ith row and jth column are deleted.
Okay, thank you.
The 2-1 minor of this 3x3 matrix is going to be the determinant of the 2x2 matrix that results after I delete the second row and the first column. So when you delete the second row and the first column, you're left with this little 2x2 matrix here. The determinant of that little 2x2 is the 2-1 minor. Okay.
Okay, thank you.
All right,
thank you.
that puts it on this video at least. So. All right. So the 3-1 minor of this 3x3 matrix again is achieved by deleting the third row and the first column. And the determinant of the little 2x2 matrix left behind then is called the 3-1 minor. So the determinant of 4, -1, -4, 8 now is going to be 4 times 8 minus -1 times -4. Therefore, it's going to be 32 minus 4, which is going to be 28. And that would be the 3-1 minor of that 3x3 square matrix there. Okay, that's all there is to finding a minor of a matrix, just by deleting the appropriate row and column and then finding the determinant of the matrix left behind. All right, now I am going to define for us what the ijth cofactor of a matrix is. The ijth cofactor of a square matrix is as follows. Now, this notation here, this C represents the word cofactor. So when you see this notation, you are to interpret this as the ijth cofactor. So in general, the ijth cofactor of a square matrix, according to this formula, is going to be equal to this: -1 raised to the I plus j power times the ij minor of the matrix. That's how you find the ij cofactor of any matrix. And since the minor of a matrix is a real number, a cofactor will also be just a real number. All right, so that's the formula for finding the ijth cofactor of a square matrix. All right, any questions about any of this so far? All right, so that's an important formula to, have in your memory banks, or at least have written down somewhere. All right, let's use that cofactor formula to find some cofactors of a square matrix. So let's give ourselves a matrix to play around with here. Suppose we have this 3x3 matrix A, whose entries are all right. Suppose I want to find this. What is this saying to find? It's saying that we need to find the 1,2 cofactor of matrix A. Now, how do we find the 1,2 cofactor of any square matrix? Well, we use our formula for a cofactor. This is going to be equal to -1 raised to the 1 plus 2 power times the 1, 2 minor. All right, now this is -1 to an odd power. And -1 to an odd power is as good as what? -1? So therefore, our 1,2 cofactor for this 3x3 matrix A is going to be nothing more than the opposite of the 1, 2 minor. Well, what's the 1, 2 minor? The 1, 2 minor is it's the determinant of the 2x2 matrix left behind after you delete the first row and the second column. So we're going to delete row 1, column 2. So I delete the first row and the second column. And when I do that, I'm left with this little 2x2 matrix, 1, 0, -5, -1. And the determinant of that little 2x2 left behind is going to be the 1, 2 minor of this matrix here. So the opposite of this determinant is the 1, 2 cofactor. So the opposite of the product of these diagonal elements, 1 times -1, minus the product of these diagonal elements, 0 times -5. So this gives me the opposite of -1. This is 0, that's gone. And +1. So 1 would be, we say, the 1, 2 cofactor of this square matrix A. So a cofactor is just a real number. Any questions how I found the 1, 2 cofactor for that square matrix A? Using the formula here for a cofactor. All right. For classwork number 1, I want you guys to do this. Using the same matrix up here, I want you to find the What is this asking you to find? It's asking you to find the what? The 3-2 cofactor. Okay, you guys go do that. I'll give you a couple minutes to find the 3-2 cofactor of that square matrix A. So using that square matrix A, I want you to find the 3-2 cofactor of that matrix A. And to do so, we use our formula for a cofactor. So the 3-2 cofactor is going to be found by taking -1 and raising it to the 3 + 2 power, 3 + 2 power, times the 3-2 minor. -1 to an odd power is always -1. So the 3-2 cofactor, as it turns out here, will be the opposite of the 3-2 minor. The 3-2 minor of this square matrix A is the determinant of the 2x2 matrix left behind after you delete the third row and the second column. So when you delete the third row, maybe I can use a different color. I delete the third row and the second column. That leaves behind a little 2x2 matrix of 2, 2, 1, 0. 2, 2, 1, 0. Got to find that determinant of this little 2x2. So it's going to be the opposite of the product of these diagonal elements minus the product of these diagonal elements. And you get +2. Hopefully somebody out there got a +2 or the 1-2 cofactor. Any questions? All right, so how are we going to use these minors, these cofactors? What are they going to be used for? Well, they're going to be used for us to be able to compute the determinant of a 3x3 matrix. The determinant of a 2x2 matrix is trivial, but for a 3x3 matrix, it's more involved. And for a 4x4 or 5x5 or higher dimension matrix, it's even more cumbersome. All right. So how would we find the determinant of in general an n by n matrix using cofactors? Well, step number 1 is we need to choose a convenient row or column to expand about. Now, ladies and gentlemen, to minimize the amount of work that you will have to go through to undertake this, you want to make sure that you always try to choose a row or a column that has the most zeros in it. Because by doing so, you will minimize the amount of work you're going to have to go through to crank out the determinant of a square matrix. So always try to choose a row or column that has the least number, that has the most number of zeros in it. Step number 2, you want to multiply each entry in the selected row or column by its corresponding cofactor. And in step number 3 is you want to sum up all the products that you've obtained in step number 2, and the sum of all these products then will be the determinant of the square matrix. So that's in general how you find the determinant of a n by n square matrix, by expanding about a row or a column using cofactors. And this is the method that's shown in your textbook. So those are the steps. And I'll leave that up there for a minute or so. So you want, whatever you want to do with this, and then we'll look at an example. All right, let's put it to practice. Give ourselves a matrix to illustrate this procedure here. So, given some matrix B, I'm going to use a matrix B this time, prior to that. Suppose matrix B is this 3 by 3 matrix here. And suppose the instructions say to do this. What is this saying to find? What does this mean? What is that telling us to find?
Find the determinant of B.
That's right. Find the determinant of this 3 by 3 matrix by using cofactors. Expanding about a row or column. Now, again, to minimize the amount of work, in reality, it doesn't matter which row or column you choose to expand about. It's entirely up to you. You'll get the same determinant either way, no matter which one you choose, as long as you do things correctly. But if you want to minimize the amount of work you have to go through to do so, you might want to choose a row or column that has the most zeros in it. Notice a wise choice would either be to choose row 2, expand about row 2, or expand about column 3, because those row 2 and column 3 have a 0 in it. That'd be a wise choice. My choice is I'm going to expand about column 3. So I'm deciding to expand about column 3. So therefore, here's how we find the determinant of that matrix. Expanding about the third column right here. I'm going to take the 1, 3 entry, the row 1, column 3 entry, which is a 2, and multiply it by the 1, 3 cofactor. Plus, I'm then going to take the 2, 3 entry, the row 2, column 3 entry, the 0 here, and multiply it by the 2, 3 cofactor. Plus, I'm going to take the 3, 3 entry, the row 3, column 3 entry, which is a -1, and multiply it by the 3, 3 cofactor. One of these cofactors we do not even have to concern ourselves with. Which cofactor do we not even have to bother with? We don't even have to deal with what cofactor.
The middle one.
Yeah, because it's going to go to 0 anyways. That's why it's wise, ladies, I'm going to choose a row or column that has the most zeros in it. It will alleviate and minimize the amount of work you got to go through to compute the determinant of a square matrix. We don't have to even worry about this. All right. All we got to worry about is 2 times the 1, 3 cofactor. What is the 1, 3 cofactor? Well, that's going to be -1 raised to the 1 + 3 power times the 1, 3 minor. plus a negative 1, I'll just say minus 1 times the 3 cofactor, which by the formula is negative 1 raised to the 3 plus 3 power times the 3 minor. All right. Now, negative 1 raised to the 4th power is positive 1. This is going to be a positive 1. Positive 1 times 2 is 2. Negative 1 raised to an even power, the 6th power, is a positive 1. This will be positive 1 times negative 1 times the 3 minor. All right, so this is all we have to do to compute the determinant of this 3 by 3 matrix above. So it's 2 times the 1 minor. What's the 1 minor? The 1 minor is the determinant of the matrix that's left behind after deleting the first row and the third column. So we delete the first row and the third column, and that leaves behind this little 2 by 2 matrix. 1, negative 3, negative 5, 5. 1, negative 3, negative 5, 5. Just like that. See that? This is the 1 minor for that matrix. The 3 minor is found by taking the determinant of the 2 by 2 matrix left behind after we delete the third row and the third column. So now we will delete the third row and the third column. And that leaves behind the 2 by 2 matrix 2, 4, 1, negative 3, whose determinant then would be the 3 minor. So we have to find the determinant of this little 2 by 2 matrix 2, 4, 1, negative 3. That is the 3 minor. This is all we got to do now. All right, so we got 2 times, what's the determinant of this 2 by 2 matrix? It's going to be 1 times 5. Subtract negative 3 times negative 5. Minus the determinant of this 2 by 2 matrix is going to be 2 times negative 3. Minus 4 times 1. All we got to do is go through the arithmetic and we'll have the determinant of this 3 by 3 matrix B. This is going to be 2 times, this is 5 minus, what is this? This is 5 minus 15, which is negative 10. This is going to be negative 6 minus 4, which is negative 10. It's going to be negative 20 plus 10, and therefore you get negative 20, you get negative 10. So negative 10 then is the determinant of that 3 by 3 matrix B. And we're done. Any questions how using cofactors and expanding about the third column, I found the determinant of the square matrix B. Any questions how I went about doing that? Expanding about the third column. Now, you could expand about any other row or column and you would still get the same determinant. In fact, for classwork number 2, I'm going to have you demonstrate that. So classwork number 2, I want you to find the determinant of matrix B again up there by expanding about row 2 using cofactors. So let's see if you can try this now. Using cofactors and expanding about the second row of that matrix B up there, I want you to find the determinant of matrix B. And when you get done, it had better come out to be negative 10. Okay, go ahead and do that. I'll give you a couple minutes to find the determinant of matrix B using cofactors, expanding about row number 2. Does anybody need to see the original matrix or did you write it down? The original matrix is right here. 2, 4, 2, 1, negative 3, 0, negative 5, 5, negative 1. Okay. All right, go ahead and try to find that determinant. And there you go. That would be finding the determinant of matrix B by expanding about the second row of that matrix. And notice you don't have to worry about the 2-3 cofactor here. It drops out. Did anybody get that correct? Are we able to show that this expansion is the same as the previous expansion, yielding the same determinant?
Yes.
It doesn't matter what row or column you expand about. If you do things correctly, you should crank out the same determinant for the matrix. It's just that, again, always try to choose a row or column that has the most zeros in it. That minimizes the amount of work you have to do. Okay. Now, this next problem here, ladies and gentlemen, should take about no more than 5 seconds to do. You ready? All right, what's the determinant of this 3x3 matrix A?
0.
0. It's 0. All you gotta do is expand about the first column, and you're gonna get 0. I guarantee you'd get 0 no matter what other row or column you choose to expand about. Why not expand about column 1? It's the easiest one to work with. All right. Now, this is a well-known fact. Remember last Thursday, when we were solving systems of equations using the matrix inversion method by finding the inverse of a square coefficient matrix, okay, and then solving a matrix equation? Well, this is a well-known fact. I think I indicated this last week, but now I'm making this official. And n by n matrix A has an inverse, A inverse, if and only if the determinant of matrix A is not equal to 0. In order for a square matrix to possess an inverse, its determinant has got to be some real number other than 0. It cannot be equal to 0. If the determinant of a square matrix is equal to 0, then the square matrix does not have an inverse matrix. It cannot be inverted. We say it's non-invertible or it's a singular matrix, in which case the system of equations will not have any solution. So this is very important to note. Matrix is only invertible or non-singular or has an inverse provided its determinant is not equal to 0. All right, now that brings us to the summit of this section. And the summit of this section is solving systems of linear equations using what's called Cramer's rule. Cramer's rule, in honor of the person that came up with this method. All right, here we have a system of 2 linear equations and 2 unknowns. Here's another equation in the system. Where the A, B, and C's are just real numbers, X and Y's are the variables. All right, so how can we, using this rule called Cramer's rule, solve this system of 2 linear equations and 2 unknowns for its ordered pair solution? Well, as we can use Cramer's rule, and this is how Cramer's rule works in general. First, we have to compute a determinant called D. D is a determinant of the left-hand side coefficient matrix of the system. So D is going to be the determinant of A1, B1, A2, B2. That's the determinant we call D, the coefficient determinant, if you will. Then we find a determinant called D sub X. D sub X is the determinant of the 2x2 matrix that results after the right-hand side constants come over and replace the X variable coefficients. In other words, this constant C1 is going to replace A1, C2 will replace A2, and we leave B1 and B2 alone. That's the determinant called D sub X. Finally, we have to compute one more determinant, which is d sub y, which is the 2 by 2 determinant of the matrix that results after replacing the y column coefficients with the right-hand side constants. That's to say C1 replaces B1, C2 replaces B2. A1 and A2 remain intact. Finally, to find the x and y coordinates is very simple now. To find the x coordinate it's just going to be the ratio of the determinant d sub x to the determinant d. To find the y coordinate of your ordered pair solution, it's just a ratio of the determinant d sub y over the determinant d. This is called Cramer's rule for solving a system of linear equations using determinants. Now, Cramer's rule also can be extrapolated to solve larger systems. Systems of 3 equations and 3 unknowns, 4 equations, 4 unknowns, 5 equations, 5 unknowns, 100 equations, 100 unknowns. Okay, but this it works the same way. It just means that you have larger determinants to compute. If I give you a larger system of equations to solve, like a system of 3 equations and 3 unknowns to solve, I'll just let you use your calculator to crank out the determinants of the 3 by 3 matrices. Okay? But this is Cramer's rule here. Let's see if we can apply Cramer's rule to an example. Solve by Cramer's rule. This system of 2 linear equations and 2 unknowns. And we do have umpteen number of ways to check our answer to make sure we got the correct ordered pair solution. There's so many different ways we've shown ourselves how to solve these systems of equations. But using Cramer's rule, here we go. First, we're going to find this 2 by 2 determinant called D, which is the determinant of the left-hand side coefficient matrix. Here we go. Then the determinant d sub x is going to be the determinant of the 2 by 2 matrix that results after replacing the x coefficients with the right-hand side constants. So 4 replaces negative 11, 6 stays intact, negative 3 replaces 2, negative 5 stays intact. Finally, we need to compute the determinant d sub y, which is the determinant of the 2 by 2 matrix formed by replacing the y coefficients with the right-hand side constants. Negative 11 remains intact. 6 is replaced with 4. 2 remains intact. Negative 5 is replaced with negative 3. All we got to do is evaluate these 2 by 2 determinants, and then we can crank out the ordered pair solution. First of all, let's find D. It's going to be negative 11 times a negative 5. Subtract 6 times 2. Careful with all your signs. Signs are always a killer. So we got 55 minus 12. And what's 55 minus 12 on a good day? I believe that's 43. D sub x is going to be 4 times negative 5 minus 6 times negative 3. That's going to be negative 20 plus 18. Which is negative what? Is that negative 2? Negative 2. D sub x is negative 2. D sub y, evaluating this 2 by 2 determinant, -3 times -11, subtract 4 times 2 is 33 minus 8, which is 25. So after having found those determinants, we can find the x coordinate. The x coordinate is d sub x divided by d, which is going to be -2/43. That's your x coordinate. Your y coordinate of your ordered pair solution is the ratio d sub y over d, which is going to be nothing more than 25/43. And we're done. So therefore, our ordered pair solution is messy. It's -2/43, 25/43. But that would be the ordered pair solution of that system of two linear equations, two unknowns, whereby we solved it using Kramer's rule and determinants. Any questions how Kramer's rule works? That's called Kramer's rule, ladies and gentlemen. What do you think about it? Pretty cool. Pretty neat, huh? Okay. Now, please do look over the examples that are laid out in this section 6.5, as your author will walk you through an example of solving a system of 3 linear equations and 3 unknowns using determinants. Okay, and I think your author actually shows you using cofactors how to find those 3 by 3 determinants manually. I won't, have you probably doing that manually. I'll probably just let you use your calculator. But you still should be familiar with how cofactors work and how expanding on a row or column can crank out a determinant of a square matrix in a manual sense. Okay. Now, being a virtual course, I can't come home and police over you and make sure that you're doing things manually when you really should be doing a lot of this manually, so you don't cheat yourself. That's the thing with these virtual classes, ladies and gentlemen, that I'm warning you about, is because we're working virtually, we don't have any supervision, okay, as we would in a classroom. And so my word of advice is just make sure you don't cheat yourself and that you are able to do these problems, some of these problems manually, and also check your answers on your calculator, but make sure you can also do them manually. That's important. Here's why. Because someday if you go back into the classroom, okay, if you've been sliding yourself outside of the classroom all these months and years with this virtual environment, then you might be a fish out of water. So just be careful. I know if I was a student in this class, I would definitely do things manually and make sure I could do things manually. But I would also check my answers on my calculator too. All right. And there's times, when the problems are so large, like for huge problems, you just want to use your calculator. Okay. But I'm talking for systems of 2 equations, 2 unknowns, maybe even finding a determinant of a 3 by 3 matrix manually by expanding by a row or column. Make sure you can do those things manually. All right. All right. That's my little lecture for today, or my little advice to you. Okay. Now we're done with that section. That closes the door on chapter 6. All we got is one more chapter to deal with in Math 130. So we'll begin with section 8.1. And ladies and gentlemen, we are going to introduce ourselves to what are called sequences in math. Sequences and series. Mathematical series are very powerful and they are used a lot in higher level math. For instance, mathematical series are used to solve differential equations. If you take that course here at Mott, you will, towards the end of the course, learn how to use infinite power series to solve differential equations. Series are also used to program calculators and computers. For instance, when you hit your e to the x button and you put something in for x, like you type in 2 and then hit your e to the x button, your calculator is taking e, this base e, and raising it to the 2nd power. How does your calculator do that? You ever wonder about that? Well, behind the scenes, ladies and gentlemen, somebody programmed the power series for e to the x power. And it is this power series right here. This is called a series in mathematics. Okay, the sum of terms of a sequence is a series. So a computer programmer programmed in this particular power series related to this key, so that when you type in a number 2, your computer takes the 2 and replaces the 2 in this power series, and it adds up so many terms of this sequence. The more terms it adds up, the more accurate approximation you're going to have. But power series are very useful in programming computer functions and calculator functions. Another area where series are used is something called Fourier series, in honor of Joseph Fourier, a French mathematician. Fourier series are invaluable, like in electrical engineering. For instance, if you have an oscilloscope and you're measuring the real-time change in voltage or current across the electronic component, enough on your oscilloscope, you get like a sawtooth wave like this, where the voltage is, basically alternating in time like this, both in magnitude and maybe even polarity, positive and negative voltage. All right, Fourier series is a nifty way of modeling the sawtooth wave structure according to an infinite power series, where you sum up a large number of sine and or cosine functions. Okay, so Fourier series is a way of modeling the sawtooth wave structure, and then once you model it according to a power series, you can then use that power series to make predictions or forecasts as to what the voltage would do under certain other future circumstances. So power series, ladies and gentlemen, are used a lot in higher level math. Okay, you're going to run into them a lot if you get into engineering, any sort of engineering. Even here at Mott, if you get into calculus 2, they're going to have you work with power series. Okay, they're going to have you work with what are called Maclaurin or Taylor power series in calculus 2. All right, so you will see series again. All right, so don't think that they're just a total waste of time. They do have a lot of very important applications. Okay. All right, so definition. Let's start off with the definition. What's a sequence in mathematics? A sequence is, it's a function whose domain consists of non-zero integers. So the domain of a sequence consists of like, wait a minute, consists of non-negative integers. I meant non-negative integers. Please do replace that here. Non-negative integers. So 0, 1, 2, 3, 4, 5, 6. That's the domain of a sequence. Okay. All right, here's an example of a sequence. 2, 4, 6, 8, 10, 12, ... What do these dots mean here in this sequence? What do you think the dots mean? Dots. What is it?
On forever.
That's right. So this is called an infinite sequence. Infinite sequence. Okay. Now, the first term of this sequence, symbolically, you could say it's the term f sub 1, f of 1. F of 2, the second term of the sequence, you could say is 4. 6, we could say is f of 3. F of 4 is the fourth term, etc. By using this notation, it's showing that this really is a function. Okay. You put a positive integer into this function, and out comes the value of the sequence here. And of course, this goes on and on and on. All right. Does a sequence always have to be infinite? The answer is no, it does not. You can have finite sequences also. So an example of a finite sequence would be one like this, 10, 5, 0, -5, -10, -15. This is a finite sequence. It consists of 1, 2, 3, 4, 5, 6 terms. Okay. All right. Here's another finite sequence here. -1, 2, -1, 2, -1, 2, -1. This is a finite sequence. And notice the signs of these terms alternate between positive and negative, or negative and positive. Because of that, we would call this an alternating finite sequence. You can also have alternating infinite sequences too. To say alternating means that the signs of the terms toggle back and forth, okay, from a negative to a positive, negative to positive, negative to positive. The alternating current or voltage that comes out of your wall outlet on your house that's generated by a power plant far away alternates in polarity, positive and negative polarity, 60 times per second, called 60 hertz, 60 hertz. So the polarity of that signal changes between positive and negative real quickly, 60 times every second. That shows you how fast the polarity changes. Can you imagine that changing from a positive, negative, positive, negative, positive, negative, positive, negative, positive, negative, 60 times per second? That's amazing. That's called alternating current. Okay. That's what comes through most of our outlets in our house. All right. Here's an example of an infinite sequence. And this is, of course, an infinite sequence. But you know, in reality, ladies and gentlemen, we don't use like functional notation when working with sequences. It's not really used in all your textbooks you're going to look at. What you're going to be looking at is normally we like to define the sequences as being like a sub n, lowercase a sub n, where this is the first term of our sequence. This is the second term of our sequence. This is the third term of our sequence, fourth term of our sequence, et cetera, et cetera, et cetera. Okay. Or there's nothing sacred about using a. I mean, you could just as well use like lowercase b sub n to denote this sequence, where in this case, this would be your first term, then your second term, then your third term, then your fourth term. Okay. But this is usually the notation that they use. They usually use a little subscript notation on a lowercase letter to represent sequences. Don't get me wrong, it's still a function. It's still like putting 1 into a function and out comes 1,000, putting 2 into a function, out comes 2,000, et cetera, et cetera. But that's the notation that they generally use. All right, there's 2 ways to represent sequences. The first way is called an nth term rule. Nth term rule. Or sometimes we just shorten it up and call it an nth rule. An nth term rule is actually an equation that instructs us how to find any nth term of a particular sequence. This is an example of an nth term rule for a sequence. It will generate any term of the sequence. In other words, what would be the first term of the sequence? Well, it's easily found by letting n be 1. Put 1 in wherever you see n in the definition of this sequence in its nth term rule here. And then you just go through and crank out the output, which would be -1. The second term of the sequence is found by letting n be 2 in this definition, which is going to be 23, et cetera, et cetera, et cetera. That's called an nth term rule. The nice thing about an nth term rule is that you can easily jump to any term of the sequence very quickly. Suppose I wanted to find the 100th term of this sequence. Well, it's easy to do. Just replace n with 100 and crank out the result. So 100 squared is going to be 10,000 times 3, which is 30,000. And 30,000 minus 4 is going to be what? What is 30,000 minus 4? 29,990 what? 6, I believe. Is that correct? Everybody see that there? All right. So an nth term rule is really easy, ladies and gentlemen, to determine any term of a sequence very quickly just by replacing the variable in the rule. Usually it's an n variable. Not always, but usually. Could be like a k variable or I variable. Normally it's n. That's why we call it an nth rule. So that's a way of determining what a sequence or how to generate any term of a sequence. All right. So suppose we wanted to write the first 4 terms of this sequence here, b sub n defined as this nth term rule to be this right here. So to write the first 4 terms of this sequence, we let n be 1. And this will find the first term, which is 5. Then we let n be 2. Second term is going to be 7. Then we let n be 3. And next term is what, 9? And the fourth term is found by letting n be 4. What do you think the fourth term is going to be based on the pattern we have here? What do you think? Looks like we're adding 2 to move to the next term, correct? So it should be what, 11? And sure enough, it is 11. All right, so we've listed the first 4 terms of that sequence using its nth term rule, called an nth term rule. All right, so an nth term rule is a very popular way of finding any term in a sequence. Suppose I have another sequence defined to be c sub n, which is -1 to the nth power times 2 times n. And suppose I want to find the first 4 terms of the sequence. Okay. So the first term is found by letting n be 1. -1 raised to an odd power is always -1, so this will be -2. Second term is found by letting n be 2. -1 to an even power is always +1, so this is just going to be 4. And then the third term, letting n be 3. We're back to a -6. And then finally, the fourth term of the sequence, letting n be 4. Back to a +8. So I've written found the first 4 terms of the sequence. And by the way, this happens to be a what? An alternating sequence. Do you agree? Alternating, because its sign alternates. So that's an alternating sequence. So any questions how given an nth term rule of a sequence, we can generate any term of the sequence if requested? Nth term rule. Notice with an nth term rule on the right of the equal sign, you always see an expression in n. Always an expression in n. Okay. How does the graph of a sequence, yes, that's right, you can graph terms of a sequence. How does the graph of a sequence differ from the graph of a function? Anybody want to take a wild guess? I'll give you a hint, domain. So suppose I have a sequence defined to be a sub n, which is n squared. And I have this function, f of x is equal to x squared. How do the graphs differ? This is your n-axis, your a sub n axis. And for this guy here, this is your x-axis and your f of x-axis. Both are functions. Both of these are functions. But how does the graph differ? Well, if I found the first term of this sequence, I would have what? 1 squared, which is 1. Therefore, I generated the ordered pair 1, 1. If I find the second term of the sequence, I put 2 in for n, I would have 2 squared or 4. I generated the ordered pair 2, 4. The third term of the sequence is found by letting n be 3, in which case I got 3 squared, which is what, 9. So I generated the ordered pair 3, 9. What am I going to see for the graph of this sequence here? Am I going to see a continual curve or just discrete points? What do you think? 1, 1. 2, 4. And then 3, 9. Way up here. You agree? This is the graph of the first 3 terms of the sequence. Now, what's going to be the graph of the function though? Remember, for a sequence, the domain is just what? The non-negative integers, usually starting at 1. Sometimes sequences start at 0, but most of the time they're going to start at 1. 1, 2, 3, 4, etc. But what's the domain of a function though? What's the domain of this function? The domain of this function is all real numbers, including decimals and fractions, correct? So for the graph of f of x equals x squared, this is just going to be a continual what? Curve, no breaks in the graph. So you can see the difference between the graph of a sequence and the graph of a function. The graph of a function, because its domain consists of all real numbers, fractions and decimals, is going to be a non-broken curve. But the graph of a sequence is just going to be the graph or plotting of discrete points. That's the difference, because its domain only consists of non-negative integers. This domain does not consist of decimals or fractions. That's the main difference between the two. All right, there is another way to represent functions. Not only do we have an nth term rule way, but ladies and gentlemen, the second way to represent a function is to use what's called a recursive definition. Recursive definition. Usually when we have a recursive definition that characterizes a function, we have to jumpstart the sequence by giving you the first term or the first couple of terms. So if I tell you the first term of a sequence is 4, then I give you a recursive definition to crank out any subsequent term of this sequence. This is called a recursive definition. How does a recursive definition differ from an nth term rule definition? Well, with an nth term rule definition, you always see an expression in n. Always an expression in n for an nth term rule. But for a recursive definition, you always see, okay, a previous term in the sequence on the right side of the equation. The n-1 term is the term that's previous to the nth term. Do you buy that? Is that true? Here's the first term, second term, third term of a sequence, fourth term of a sequence, dot, dot, dot. Here's the n-2th term, the n-1th term, the nth term, the n+1th term, the n+2th term, etc. Are we clear on that, ladies and gentlemen? See that there? Notice the n-1 term precedes the nth term. The n-2 term precedes the n-1 term. The n+1 term follows the nth term. The n+2th term follows the n+1th term. Everybody see that there? So how do we find the next term of the sequence? We find it by taking the previous term and multiplying it by 2 and adding 1. Suppose I wanted to find the first 4 terms of this sequence defined recursively. How would I do that? Well, we know the first term is 4. Now to find the second term, I'm going to have to let n be 2 in my recursive definition. So my second term is going to be 2 times my 2 minus 1th term plus 1, which is to say 2 times my first term plus 1. But my first term is 4. So I can replace the first term with 4. And then I crank out my second term, which is 9. Now to find the third term of this sequence defined recursively, I put 3 in for n in my recursive definition. So my third term is going to be 2 times my 3 minus 1th term plus 1, which is really saying 2 times my second term plus 1. Oh, but what's my second term? My second term is 9. So 9 goes in for my second term. So my third term is going to be 2 times 9 plus 1, which is going to give me 19. Finally, to find the fourth term of this sequence defined recursively, I put 4 in to my recursive definition for n. So my fourth term is going to be 2 times my 4 minus 1th term plus 1. Which is to say 2 times my third term plus 1. But what's my third term? Oh, my third term is 19. So my fourth term is going to be 2 times 19 plus 1, which is going to be 39. Does everybody understand how we are generating terms of this sequence using its recursive definition? This is not an nth term rule, that's a recursive rule, recursive definition. Now I have a question for you. Suppose that I wanted you to find the 100th term of this sequence. Would that be easy or difficult to do? If I wanted you to find the 100th term. Which method would be easier to find the 100th term of a sequence? The nth term rule method or the recursive definition method? What do you think? Anybody? What would be the easier way to go to finding the 100th term of a sequence? Using the nth term rule way or the recursive definition way? Well, to find the 100th term, in order to find the 100th term, we're going to need to know the 99th term. But in order to know the 99th term, we're going to need to know the 98th term. But to know the 98th term, we're going to need to know the 97th term. But to know the 97th term, we're going to need to know the 96th term. Oh, I think we're starting to see what's going on. Dot, 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 all the way down to we're going to need to know the second term and then also the first term. Recursion is extremely cumbersome if you want to find a term that's way out there for a sequence to find recursively. Because you got to know every previous term, all the way back to the first term. Now, a computer could find the 100th term recursively within a fraction of a second. In fact, that's one popular way of writing computer programs is called recursion. That was the least favorite method as far as I'm concerned when I was in computer science. I did not like the recursion way of writing code because recursion is hard to understand, but it's extremely efficient for a computer to perform things recursively, okay? But the nth term rule makes a lot more sense as far as us humans are concerned. We can relate to it better than recursion. All right. 148. Ladies and gentlemen, do you think sequences have any use in the real world? Or is this just something that we cook up to keep you off the streets on a Saturday night? Well, believe it or not, sequences actually have use in the real natural world. Let me show you an example. This is actually in your textbook. It's called the Fibonacci sequence. The Fibonacci sequence is defined recursively here, where they give you the first two terms of the Fibonacci sequence. And to find any subsequent term, you have to use the term that's 2 back plus the term that's 1 back. Okay, in other words, to find the third term, we have to know the first term and we got to know the second term. To find the fourth term of a Fibonacci sequence, we have to know the second term and the third term. To find the 100th term of a Fibonacci sequence, we got to know the 98th term and we got to know the 99th term. This Fibonacci sequence is in honor of a mathematician by the name of Fibonacci, who came up with this sequence. And would you believe, ladies and gentlemen, that honeybee reproduction follows the Fibonacci sequence to a T? Go figure that, huh? Here's the first several terms of Fibonacci sequence: 1, 1, 2, 3, 5, 8, 13, 21, 34, 55, 89, etc., etc. Notice this 2 is obtained by adding the 2 previous terms together. This 3 is obtained by adding the term 2 back to the term 1 back. 5 is obtained by adding this 2 and this 3. 8 is obtained by adding the 3 and the 5. 13 is obtained by adding the 5 and the 8. 21 is obtained by adding the 8 to 13. 34 is obtained by adding 13 and 21. That's how the Fibonacci sequence works. You know, I am told, and I didn't know this, and I found this out when I seen it in your textbook. Interesting. I had no idea about this, but the honeybees, ladies and gentlemen, to produce a honeybee, it's only necessary for a female to lay an egg. And this egg does not have to be fertilized, and a male will result. But in order for a female honeybee to come into existence, a female's egg has to be fertilized by a male's egg to produce a female. So let's look at the several generations of where a male comes from in a honeybee hive. A male comes from some female, but this female came from some male and female. This male came from some previous female. This female came from some previous male and female. This male came from some female. This female came from some female and male. And you could go back on and on and on. Now notice how the number of bees follows the Fibonacci sequence. 1 bee, 1 bee, 2 bees, 3 bees, 1, 2, 3, 4, 5 bees. What would be next after 5 bees? Then it would be 8 bees, 13 bees, 21 bees as you go further and further back into the generations of these bees. That's pretty amazing, isn't it? So I only have one question for you. What came first? Did Fibonacci sequence come first and then the honeybees mimic the sequence in generating the way they do? Or did the bee generation come first and then Fibonacci just observed the bee generation and came up with the Fibonacci sequence? In other words, that's very interesting to try to find out on which come first here. Fibonacci sequence or the way bees multiply. Interesting. Don't know. Might be something I might want to investigate. Okay, what came first? It's like, what came first, the chicken or the egg? Interesting. Fibonacci sequence, just one among many uses in nature where nature seems to love to model itself according to sequences of various types. All right, sometimes sequences actually have this function involved. It's called the factorial function. And the factorial function will once again rear its presence deeper in this chapter when we start learning how to count by computing what are called combinations and also permutations. Okay, combinations and permutations are studied in a course called combinatorics. And ways of enumerating things is used to compute probabilities. Okay, factorial function, ladies and gentlemen. How do we read this notation? We read this as n factorial. And n factorial by definition is n times n minus 1 times n minus 2 times n minus 3 times n minus 4 times n minus 5 times ... all the way till you eventually get down to 2 times 1. So let's try one out. Now, I don't have time to explain this, ladies and gentlemen, but you just have to accept it. 0 factorial on planet Earth is defined to be equal to 1. I know that sounds bizarre, but it's true. And it's accepted worldwide, okay? So 0 factorial is 1. What's 1 factorial? 1. What's 2 factorial? That's 2 times 2 minus 1, or 2 times 1, or 2. What's 3 factorial? That's 3 times 3 minus 1 times 3 minus 2, or that's 3 times 2 times 1, which is 6. What's 4 factorial? That's 4 times 3 times 2 times 1, which is 24. What's 5 factorial? That's 5 times 4 times 3 times 2 times 1. Factorials grow very quickly, as you can see. 5 factorials are also expressed as 5 times 4 factorial, which is to say 5 times 24, which is to say 120. Factorials grow very quickly. On your calculator, where does the factorial function hang out? Well, if you hit your math button and then go over to your probability menu, PRB, you'll see the factorial function down there. Try this out on your calculator. Can your calculator handle a number that's as large as 50 factorial? Type in 50, hit math, go to probability, grab the factorial, hit enter. What do you get? Somebody read off what you got on your calculator when you took 50 factorial. That's 50 times 49 times 48 times 47 times 46 times 45 times 44 times 43 times 42 times 41 times 40 times 39 times 38 times 37, all the way down to times 2 times 1. Big number. What'd you get? What'd your calculator report? Anybody? 50 factorial. I think somebody in my face-to-face section this morning came up with like 3 times 10 to some horrendously large power. 3, it's got some decimal, some digits, and it says E what? What's the exponent?
64.
64. 3 times 10 to the 64th power. That's what that's saying. That's a large number. That's 3 with 64 zeros after it. If you had this amount of money sitting in your bank account, would you be here right now? Well, I don't know. You might be bored with life. Do you agree? Well, anyways, ladies and gentlemen, that's a very big number. That's a very quick way to determine the size of numbers that your calculator or computer can handle is by subjecting it to the factorial test. Now, 100 factorial. Try 100 factorial on your calculator. Can your calculator handle a number this big, which is humongous? That's 100 times. This is huge. This is 100 times 99 times 98 times 97 times 96 times 95 times 94 times 93, all the way down to times 2 times 1. That's a horrendously large number. Can our calculator handle that, the TI-84?
No.
No, it says overflow, or what does it say? Error or what?
Error.
Error, overflow. That's horrendously large. Okay. See, certain computers and calculators, computers can only handle numbers so large. That's true for supercomputers too, although they can handle numbers a lot larger than your TI-84 calculator can. But this is still a very big number. All right. And we're getting on the astronomical scale now is where we're approaching. Okay. So, ladies and gentlemen, is it possible for an nth term rule of a sequence to have the factorial function in it? The answer is yes, it is. I'm not going to, go ahead and play with this anymore, but I'm just going to show you quickly because we're running out of time that yes, sequences can be defined using factorials. It's possible. Okay. All right. Now, here's what we're going to do to occupy the rest of our time here. We're going to just look at how to find the nth term rule for a sequence, and then we're going to introduce ourselves quickly to a series, what a mathematical series is. All right, let's look at this sequence here, where I give you the first several terms. It's an infinite sequence, and I want you to find the nth term rule for the sequence. Now, remember, this is your first term, this is your second term, third term, fourth term, fifth term, sixth term. Question, what would be the nth term? You have to pay attention to the term index and the actual term value. In other words, what rule could we establish such that we would do something to 1 to make it become 2, something we can do to 2 to make it 3, something to do to 3 to make it 4, to make 4 become 5, to make 5 become 6, make 6 become 7. What rule would that be? Can you see it? The relationship between the term value in the sequence and the term index. What relationship exists? Do you see a pattern of any sort here? How does 1 relate to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, 6 to 7? Anybody?
Would it be like AN plus 1?
Yeah, it looks like the term of the sequence is always 1 ahead of the term index. Do you agree? 2 is 1 more than 1. 3 is 1 more than 2. 4 is 1 more than 3. 5 is 1 more than 4. 6, 1 more than 5. 7, 1 more than 6. So therefore, the nth term is going to be 1 more than what? N. That would be the nth term rule that would generate any term for this sequence. That's its nth term rule. Everybody see that there? That was a pretty easy one. Unfortunately, it's not always that easy to determine an nth term rule for a sequence. Sometimes you're scratching your head for hours or even days trying to figure out what it is. Let's try this one. This is your first term, second term, third term, fourth term. Okay, what's my nth term? What do we do to 1 to get 3? What can we do to 2 to get 9? And can we apply the same rule to 3 to get 27? And apply the same rule to 4 to get 81? What do we do? Anybody see anything here? Any pattern? How does 1 become 3, 2 become 9, 3 become 27, 4 become 81? Hey, I'll tell you what, this might help. You agree that all these terms in this sequence happen to be what? Multiples of what number? Aren't they multiples of 3? 3 is 3 to the first power. 9 is 3 squared. Ah, here it comes. 27 is 3 cubed. 81 is 3 to the fourth. Notice we have to raise 3 to the index power to generate the term. So the nth term is going to be 3 to the what? Nth power. That would be how you generate any term for this sequence. And we see what we're doing here. Given a sequence, we're writing its nth term rule. All right, so far those weren't really that bad. How about this one? 2/3, 3/4, 4/5, 5/6. All right, what would be the nth term rule here? There's your first term, second term, third term, fourth term. What would be the nth term? Tell you what, break it up into parts. Just look at the numerators first. How does 1 become 2, 2 become 3, 3 become 4, 4 become 5? How does the numerator value relate to the index of the term? It appears the numerator is always what? 1 larger than the index of the term, correct? So therefore, the numerator of the nth term will be n plus 1. That's it. How about your denominator? How does 3 relate to 1? 4 relate to 2, 5 relate to 3, 6 relate to 4. Looks like your denominator is how much more than the index of your term?
2.
2 larger, 2 larger. There you go. There's your nth term rule. That would generate any term in that sequence. Is this making any sense? How, given a sequence, we're writing its nth term rule? Some are pretty easy, but some, like I said, can be a little bit more difficult than you think. So far, these have been not too bad. Okay. Too bad. Like I said, some could be more challenging. 1/5, -4/25, 9/125, -16/625. This is your first term, second term, third term, fourth term. What would be your nth term in general? First of all, notice we have an alternation in sign. We go from a positive to a negative, back to a positive, then to a negative, back to a positive, positive, negative, positive, negative, positive, negative. This is an alternating infinite sequence. How do we account for the alternation in sign? Notice the odd terms are positive. The even terms are negative. How do we account for that? Well, we got to have -1 raised to some sort of a power in n. What would be that power in n? Anybody want to take a guess? What power do you have to raise -1 to have the first term be positive, the third term be positive, the fifth term be positive, etc.? But the second term must be negative, and the fourth term must be negative, and the sixth term, and the eighth term, and the 10th term must be negative, etc., etc. What do you think? Well, -1 to an odd power should be -1, yet it's +1. How do I make an odd power? How do I make an odd number become an even number? Just maybe add 1 to it? If I add 1 to an odd number, do I not get an even number? And if I add 1 to an even number, do I not get an odd number? I think that might work. So ladies and gentlemen, there you go. This will account for the alternation in sign. -1 raised to the n plus 1 power. Times, what about the numerator? 1, 4, 9, 16. These all appear to be perfect what? Perfect squares. Perfect squares in the numerator. Do you agree? So how do I find my nth term numerator? It'll be n what? Squared? How about the denominator? All these numbers in the denominator are multiples of what number? All multiples of what? Of
5.
5. 5 is 5 to the first power. 25 is 5 squared. 125 is 5 cubed. 625 is 5 to the fourth. Now look at the power of 5 is raised to. 5 to the first, first term. 5 to the second, second term. 5 to the third, third term. 5 to the fourth, fourth term. Okay, so it must be 5 to the nth power. Got it. There you go. That's your nth term rule for the terms of that sequence. See how we chipped away at it one part at a time? All right. So like I said, some of those are easy, but some could be very challenging. Okay. Okay. The only other thing that remains before we close it out here today, ladies and gentlemen, is we need to talk about a series in mathematics. What's a series? Definition. A series is nothing more than the sum of, it's the sum, a series is a sum. It's a sum of terms of a sequence. That's what a mathematical series is. It's the sum of terms of a sequence. So here's an example of an infinite series where we add an infinite number of terms together of a particular sequence. That's called an infinite series. Here's a finite series, and we call this the nth partial sum. The nth partial sum, which means we add up only the first n terms of a sequence. The first n terms get added together. That's it. Plus dot, 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 plus the n minus 2th term, plus the n minus 1th term, plus the nth term. This is a finite series. So this is finite, and this is an infinite series. Okay, finite and infinite. Now there is a character that comes from the Greek alphabet. It's a sideways looking M. Anybody ever see this character before? This is called uppercase sigma. And whenever you see this symbol, it means you're going to be adding things together. All right. So if I wanted to add together the first n terms of a sequence, I could represent this sum more compactly using what's called summation notation. Uppercase sigma. And this uppercase sigma or summation notation always has an index of summation. Normally it's like the letters of I or N or K or even J. It doesn't matter what letter you use here, whether you use I, K, N, J, whatever. This is called the index of the summation notation, index. And this index starts at 1, then it increments integerally. Is that even a word, integerally? I don't know. I just threw it out there. It increments integerally until it reaches an integer value of n, and it terminates at this value here. Inside the summation notation, we're going to have what's called the nth term rule that generates terms of the sequence. This is the nth rule. I know you don't see the letter N here, you see I, but in general, we generically, regardless of whatever letter we use for the index, we always call this the nth rule in general. This is a compact way, ladies and gentlemen, of saying I starts at 1, so we'll take our first term and then I increments to 2 and add it to the second term. I increments to 3, add that to the third term, plus I increments to 4, add that to the fourth term, plus dot, 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 where I terminates at n. So our nth term is the last term we add. This is a compact way of saying this. This compact notation is called summation notation. It even rhymes, doesn't it? Isn't that cool? Summation notation. You see this a lot, and of course, in statistics and probability. You'll also see this, like I said, if you go onwards into calculus here at Mott and even differential equations, you'll see this notation here, series. This is a finite series. We're adding up the first n terms of the sequence. Could you have an infinite series represented by summation notation? The answer is yes. This particular series here is adding together an infinite number of terms of some sequence B sub n. Okay, so this is adding up an infinite number of terms of this sequence. It goes on forever. That's an infinite series. Well, we're in the home stretch now. Suppose I want you to evaluate this summation here. I want you to evaluate the summation. Well, how do we do that? Well, we are being told to add together the first 5 terms of this associated sequence whose nth term rule is right here. This is called the nth rule for the sequence. It would enable us to generate any nth term of the sequence. It literally is the nth rule. I know we're not using the variable n, but generically we still call it the nth rule. So what's the first term of the sequence? You let k be 1. So the first term would be 2 times 1 plus 3. That's going to get added to the second term where k increments to 2. 2 times 2 plus 3 plus the third term where k goes to 3. Plus the fourth term where k goes to 4. And then we terminate by adding the fifth term where k terminates at 5. So that's really saying that we're going to add together. What does this give you here? What is that? 5 plus what? 7 plus 9 plus what? 11 plus what's this? 13, I think. What does that give you? There gives you what? 12 plus 9 is what? 21 plus 11 is 32. 32 plus 13 is going to be 45. We have just evaluated that summation. Make sense? That's what we've done there. Okay. Oh, son of a gun. All right, suppose you want to go backwards. Suppose you want to write the summation notation for these series here. Now, is this going to be an infinite or finite series here? This is infinite. We have to first of all come up with an nth term rule. What's it going to be? This is your first term. First term. This is your second term. Third term. Fourth term. So how does 1 become 1, 2 become 4, 3 become 9, 4 become 16? Notice our numerators are all perfect squares. 1 squared, 2 squared, 3 squared, 4 squared. So I'll bet dollars to donuts then your nth term is going to have your numerator be n squared. Look at your denominator. How does 1 become 2, 2 become 3, 3 become 4, 4 become 5? Looks like the denominator is 1 more than the term index. So your denominator, nth term denominator is going to be n plus 1. Now that we have the nth term rule for this associated sequence, we can now write the series, the summation notation, where n goes from 1 to infinity, and our nth term rule we just slip in here, and we got it, ladies and gentlemen. That would be the summation notation to represent this infinite sum. Everybody see that there? How we did that? All right, maybe try 1 or 2 more here in the time we have remaining. I forgot to show my face-to-face section this, so I'm going to have to direct their attention to the remainder of the tail end of this lecture here. All right, let's try to write the summation notation for this series here. Notice this is a finite series as we're adding up a finite number of terms together here. First, we have to find the nth term rule. This is your first term, second term, third term, fourth term, fifth term. What would be my nth term rule? Notice we have an alternation in sign, negative, positive, negative, positive, negative. Notice my odd terms are negative. My even terms are positive. And remember, a -1 raised to an odd power, ladies and gentlemen, will give you a negative. And -1 raised to an even power will give you a positive. So therefore, since my odd terms are negative, my evens are positive, all I have to do is say -1 raised to the nth power will account for the alternation in sign. Because if n is odd, this is negative. If n is even, this is positive. We're good. Now, how about the numerator? Notice the numerators of all these fractions are 1. Why would it change for your nth term in general? It would be 1. Your denominators, notice they're all what? Multiples of 2. Where this is 2 to the first power, this is 2 squared, 2 to the third power, 2 to the fourth power, and 2 to the fifth power. So notice the denominator is 2 raised to the power equal to the index of the term. So therefore your nth term will probably be 2 raised to the nth power. There's your nth term rule that would generate any term of the associated sequence. Therefore, we bring it up and put it inside our summation operator here. We have -1 to the nth power times 1 over 2 to the nth power, where n ranges from 1 to what? 1 to 5. We summed up the first 5 terms. That would be the summation notation that we would have to write to represent that series. Is this making any sense how we're given a series and we're writing the summation notation for it in compact form? First, you got to come up with the nth term rule, which is probably obviously the most challenging part. Once you get the nth term rule, it's very easy to write the summation notation. Okay. All right. Last thing here, there are some properties of that this summation operator obeys. The summation operator says that if you're adding terms of a constant sequence together, the sum is going to be nothing more than the number of terms you added together times that constant term. So what is this first property saying? It's saying this, that if I had this series here, if I had 5 plus 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 5, how many times am I adding 5 together here? 1, 2, 3, 4, 5, 6, 7, what, 8 times? This is a way of representing the series, which would evaluate to just 8 times 5 or 40. That's what that first property is saying. So in general, when you add n terms of a constant sequence together, your end result, your sum, your resultant sum is going to be n times c. These two properties illustrate that the summation operator, sigma, preserves scalar multiplications and sums and differences. That's to say that if I have a sum of a constant times the terms of a sequence, that's equivalent to as if I bring that constant outside the summation operator, first adding the terms of my sequence together and then multiplying that sum by the constant. That's equivalent to as if I multiply each term of the sequence by the constant first and then add them together. Same result. This property is saying that the sum of corresponding terms of two different sequences can be rewritten as the sum of the individual sums of the individual sequences. So the series of a sum or difference can be rewritten as a sum or difference of series. These are all properties that the summation operator obeys. And you know, these properties are also obeyed by the derivative operator in calculus 1 and also the integral operator, the antiderivative operator in calculus. Those operators also obey these properties here. Okay. All right, so that's it, ladies and gentlemen. I have exhausted what I had to talk about today. We did finish set